Today, I want to talk about the idea of span again. This is directly related to the stuff that we've talked about most recently. Let's suppose that I have a set of vectors. There are going to be k of these vectors called v1, v2 out to v number k. Each one of these vectors is going to be a vector in Rn. So each one of these column vectors is going to consist of a column of n numbers. When I look at what we're going to call the span of these vectors, this is just the set of all conceivable linear combinations C1v1 plus C2v2 out to CKVK, where the C numbers are real numbers that you can pick any way you want to pick. For example, I might have a set of two vectors, 1, 0, 1 and 2, 1, 1. The vectors themselves are members of R3, the column vectors that have three numbers in them. The span of those two vectors is the collection of all number times the first one plus number times the second one. Terminology time. We say that a set of vectors, like that set of vectors, for example, spans Rn, R3 for our example, if every vector in Rn, R3 for us, can be written as a linear combination of vectors in the set. So I'd like to answer this question. Does that set of vectors span R3? Is it true or is it false that I can write any vector in R3 as a linear combination of those two? This is not immediately clear, so we have to look at it. I'm going to look at a linear combination of the two vectors in question and try to figure out if I believe the following statement is true or false. If you give me any vector in R3, then I can write it in that manner. Either that statement is true, in which case those two vectors will span R3, or the statement is false, and they don't. What I have to do is, I have to imagine someone giving me any vector in R3 and trying to pick the C1 and C2 to reproduce it. Select a vector in R3 with components A, B, and C, and it's important to keep in mind we are allowed to pick any numbers A, B, and C if we want, and we want to figure out whether or not there are numbers C1 and C2 that make this true. I can write this in our usual augmented coefficient matrix form if I can triangularize the coefficient part or reduce it to reduced echelon form. Then I'll be able to see what needs to be true in order for this to work out. After doing that, I'll multiply the bottom equation by -1. I'll subtract the second equation away from the third one. The last equation reads that 0 times C2 needs to be A minus C minus B. The left-hand side of that equation is always 0. The right-hand side is A minus C minus B. If a minus c minus b is 0, then the equation is true. But if a minus c minus b is not 0, then it can't be true. This answers our question, but we'll look at it in more detail in a moment. Something that might be worth mentioning is we could think of a, b, and c as being x, y, and z coordinates of the endpoint of our vector. The places where this is going to work out would be x minus z minus y equals 0, which you'll recall from Calculus 3 is a two-dimensional plane. There's going to be a plane of vectors where this will work out okay, but if you're outside that plane, you won't have any luck. Having said that, let's go looking for trouble because we now know exactly where to find it. I'm going to pick numbers a, b, and c that don't obey that equation, and I can tell you ahead of time there is no linear combination of these two vectors that will produce such a thing. If we pick a to be 4, b to be 1, and c to be 2, then a minus c minus b works out to be 4 minus 2 minus 1, 4 minus 3, which is 1, and 1 is not 0. Based on what we've said already, there is not going to be any linear combination of the original two vectors that gives me 4, 1, 2 back for an answer. Writing it out in detail, c1 times 1 plus c2 times 2 must equal 4. c1 times 0, I won't even write that down, plus c1 times 1 must be 1. c2 times 1 is 1. c1 plus c2 must be 2. We could write the augmented coefficient matrix of this, or I could observe that the middle equation tells me what C2 has to be. For this to work, C2 has to be equal to 1. But the other two equations will tell me what C1 is, and that's where the problem is at. For the vector 4, 1, 2 to be a linear combination of my two vectors, I must get the same value of C1 from both of those equations. The first one ends up telling me that C1 absolutely has to be 2 and nothing else. The last equation ends up telling me that C1 has to be 1. There's no way to make both of those things true at the same time. This set of equations has no solution. There is no way of picking C1 and C2 so that this happens. 4, 1, 2 is not contained within the span of the vectors 1, 0, 1 and 2, 1, 1. In a like manner, do the three vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1 span R3? I need to look at a linear combination of those three vectors and see if I can make it equal to any vector in R3 that I feel like. For arbitrary choices of numbers A, B, and C, will there be a way to pick C1, C2, and C3 so that this happens? Forming the linear combination, simplifying as we did it before, in order to make this happen, it would be necessary for C1 to be whatever A number we picked out, C2 to be whatever B number, and C3 be whatever C number that we picked out. The answer to the question is yes. Give me any vector in R3, and I can write it as a linear combination of these three vectors. We will say then that that set of vectors spans R3. We will say then that
In the
that
next
set of
short video,
vectors
I'm
spans
going to do
R3.
another example of this.
We will
Also,
say
we're going to
then that
introduce
that
some
set of vectors
terminology
spans
involving the words
R3.
one-to-one and onto,
We will say
also
then
more
that
formally
that
known
set of
as
vectors
injections and
spans
surjections.
R3.
And then we'll be in a
We will
position to
say
talk
then
about the
that that
inverse
set
of
of
a
vectors
matrix.
spans
Until then,
R3.
I hope everyone's having a good day,
We will
and I'll
say
talk to
then
you
that
again
that
soon.
set of vectors spans R3.